observed that air has a finite conductivity, and that if you build an electrometer even in a tight and dry bottle, the electrometer will slowly discharge. A basic electrometer is a couple of metal sheets that if you charge, they repel each other, and they stay at an opening angle, and during the discharge they close. So the electrometer measures an effect that you can measure. In the early 20th century, before the discovery of cosmic rays, but after the discovery of radioactivity. Radioactivity was discovered in 1898, while evidence that we have cosmic rays came 15 years later. So there was a window in which radioactivity was known and cosmic radiation was not. And the first hypothesis was that this radiation that you can easily see in air was coming from natural radioactivity of the Earth. So I started historically to measure this ionization in air as a function of the height, starting from simple experiments like moving the electrometer in the Eiffel Tower. But this is already kind of enough, because you have 300 meters of air, which is already some kind of substantial amount of matter, because you have to imagine that air is about 1,000 water, so 300 meters of air is roughly equivalent to 30 centimeters of water, and 30 centimeters of water are already a significant shielding. You reduce radiation by more than a factor of 10 with 10 centimeters of water. This was known even to the people in the early century, because it was very well known that alpha radioactivity was stopped even by a few centimeters of air. Beta radioactivity, it's a little bit more penetrating, but you cannot make 300 meters in air with a beta anyway. Only gamma radiation could go that way, but you would expect anyway an attenuation, even a gamma radiation. So, general ground, you would expect that if you go into the Eiffel Tower, you should get less radiation, and in fact, you don't get. You get essentially the same amount, not really, slightly lower, but not much. And but it took a while before a clear explanation came, because with the first balloon flights at the beginning of the century, up to a few kilometers from the ground, Hess discovers that the decrease stops at about 700 meters, and you start increasing again. And the reason is that actually, of course, the truth is always complex. At ground level, you have both external radiation and Earth radioactivity. So when you go up, you start losing the Earth radioactivity, but then you start to see again external radiation. So it took a while before the existence of the external radiation was understood. Hess is a smart guy and started to make some interesting measurement. The first he does is that to measure the effect both at night and during daytime, which seems to be trivial, but it's not, because it proves that this radiation does not come from the sun, which could be a typical explanation. There is plenty of radiation that comes from the sun. Again, nature is complex. But this radiation from the sun, which is called, of course, solar wind, it's very low energy and does not go through the atmosphere. So if you want to see the radiation from the sun, which is very huge, you have to go in space. If you go in space, you are dominated by sun radiation, but not within the atmosphere. within the atmosphere, you are dominated by high energy particles that come from this space and not from the sun. It takes a while before a complete understanding of the problem arrives. Actually, we still don't have a complete understanding, but of course we know much more. 1925, Millikan is the person who makes a refined experiment in which he finally proves that there is radiation from outside and that he believes it's made of gamma radiation. At that time, the detectors are purely ionization detectors. They measure the ionization in gas, so they cannot tell which particle is producing the ionization. You need a different technology to do that, and it's the development of the Wilson chamber, of the cloud chamber, in which you can see the tracks and you can disentangle gamma radiation, neutral particles, from truly charged particles. And this, the invention of the Wilson chamber has a branch which is called particle physics, because immediately you see that the particles you see, you don't know what they are. You discover the pion, you discover the muon, you discover the kaon. You don't find just protons or electrons as the physicists of the 30s would have expected. So this is also the beginning of particle physics, but this is a different chapter. What I focus today is the purely cosmic ray physics, which means what kind of radiation is arriving from the space, which energy, which flux, which origin, what in space produces this radiation. Of course, you do measurement with magnetic field, and you can measure the charge, the momentum of these particles, and you immediately see that there are particles of very high energy. In 1927, it's an important effect because it is discovered that the flux depends on latitude, which means that unless you assume that there is an isotropy that is related to the Earth equator, which does not make any sense, the most reasonable explanation is that the radiation that comes from the space interact with the Earth magnetic field, which proves that it's made of charged particles. So at least one component of the radiation that comes from space is made of charged particles that are deflected by the magnetic field of the Earth, and this explains this dependence on the latitude, because the intensity of the magnetic field depends on the latitude. If it is true, you would expect also a west-east effect, because positive charged particles are deflected on the other side as -1, and this is observed, which proves that the cosmic rays is not made in equal amounts of positive and negative particles, because of course if you have the same amount of negative and positive, the effect cancels out. But if you have positive particles, they are deflected east or west, depending on being north or south of the magnetic pole. And this effect proves in 1933 that most of the cosmic rays is made of positive particles. And another set of tests in which you put a detector in balloons that can measure the ionization of the charged particle. They prove that it's mostly proton, but not only proton. Now we know that the composition is dominated by proton, but it's made of nuclei of every charge, but it's mostly microns. In 1933, Bruno Rossi discovered the extensive showers, which means he discovers that what you observe on the ground are not particles that really comes from space, but are the secondary product of the interaction of cosmic rays in the atmosphere. And what you typically see on the ground is a shower of particles coming from the interaction of a primary proton or a primary nucleus, or a primary photon, or more rarely a primary electron that interact with the atmosphere. So if you want to see the primaries, you have to go up, or if you stay on ground, you can measure the extensive showers. Both techniques are important because in principle you would like to go up and measure the primaries, but when you go to high energy, the flux is too low to see the effect staying up. Because if you make a detector that is a few square meters, up to, let's say, 1 TeV, which is the current value of the AMS spectrometer, which is an instrument that is flying on the space station, which we will discuss later. AMS is about 4 square meters. You can see particles up to essentially 500 GeV with that. Because above 500 GeV or 1 TeV, the flux is too low and you don't have statistics. Because the flux, in terms of number of particles per square meter per second, goes down, as we will see in a moment, as close to the third power of the energy. So every time you increase the energy by a factor of 10, you decrease the flux by a factor of 1000. So low energy cosmic rays is done with instruments flying in space up to, let's say 1 TeV, it's a little bit less than that, but let's say up to 1 TeV you go in space. Above 1 TeV you have to make measurement with indirect means in the atmosphere by looking at showers in the atmosphere by some techniques that we will discuss. So the technique of the extensive air showers is the most important one at high energies. Let's say above 1 TeV or several TeVs. Actually, there is a gap. You can measure very well up to 1 TeV in space, and you can measure very well in the atmosphere up above 100 TeV or so. In the middle, it's difficult. 10 TeV, 5 TeV. It's too high energy to stay in space and too low energy to get an important shower in the atmosphere. So in the gap, you have troubles. The first real proof and the first experiment explicitly designed to observe extensive air showers was done by Pierre Auger in 1938. Do not get confused by the Auger project that is now running, which is a huge project whose name is in recognition of the work made by Pierre Auger.
Sorry, one question. In principle, so which kind of particles we have outside the atmosphere? Are protons?
The particles coming from the space are mostly protons, right, but there is an important component of other nuclei, plus electrons, plus photons. There is everything.
Okay.
Okay, but it's in small amount.
Mm-hmm.
So if you look by numbers, you are dominated by protons. But of course, there is plenty of science and plenty of physics that you can do by looking at the gamma rays, gamma astronomy, and by looking at electrons with positrons and other nuclei.
Okay.
But to do gamma, each particle requires dedicated technique, as you will see.
Yes.
Auger is the first who understands that cosmic rays provides energy that are just unthinkable for ground experiment. The first showers observed by Auger with a very small detector already show energies of 10 to the 15 electron volt, which is a factor of 1,000 more than what we can do today. Okay? And actually the cosmic rays are 5 orders of magnitude more than that. But it is immediately understood that with cosmic rays, in principle, you can do physics at very high energy. The flux.
Another question, the distribution of the cosmic rays outside the atmosphere is isotropic or anisotropic?
At first order, it's perfectly isotropic. At relatively low energy, there are anisotropies that are understood as the effect of the magnetic field of the Earth, of the solar system, and of the galaxy.
Okay.
So you observe anisotropies, which are understood as local effects due to that magnetic field. But the problem is difficult because we don't know precisely the magnetic field distribution. So these anisotropies exist. They are not completely mysterious, but they are not completely understood.
Okay.
Because a complete understanding of these anisotropies requires a complete understanding of the structure of magnetic field, which is not an easy task.
Okay.
At very high energy, you would expect anisotropies due to the sources, because you would expect that very high energy particles are not deflected by magnetic field, and they should bear the information of their sources. You should understand where they are coming from. But this is not obvious because it depends how far they are.
Perfect.
If they are local sources within the galaxy, you would expect that above 10 to the 19 you should see the sources. We do not see the sources, so likely this very high energy cosmic rays comes from much larger distance than the galaxy. And so it depends how far, because if it is, let's say, 110 megaparsec, you should see the sources. If it is more than that, you should not see the sources, because the effect of the magnetic field and of other effects that we will discuss cancel the effect. So far, we have no evidence of sources in no channel, but maybe we will. The energy can be exceedingly large. Okay, 10 to the 20 electron volt is the energy of a tennis ball concentrated in a single point. So it's close to two cosmic rays that collide and make a Planck mass. Of course, this is not the case because the cosmic rays collides with a fixed target. So the invariant mass is not that large. But anyway, the invariant mass of a 10 to the 20 electron volt proton is a factor of 1,000 larger than the invariant mass that you see. So it is still true that you can, in principle, probe energies that are much beyond the capability of the accelerators. Of course, you do it using a natural beam that you cannot control. So your possibility to make experiments is much limited with respect to what you can do at accelerators. As I told you, the flux is roughly a third the power of the energy. So you have 10 orders of magnitude in energy, essentially, from 1 GeV to 10 to the 20. And you have a span of about 30 orders of magnitude in flux. You go from kilohertz per square meter at low energy up to 1 event per century per square kilometers at very high energy. So the technique you use to study this very broad energy spectrum is very different because, of course, if you have a huge flux at low energy, maybe a small detector like that flying is enough. But if you want to study the highest energies, you need huge detectors, like, for example, the Piaget observatory that we will see in a moment. What is a shower? Well, I assume you know, but I go quickly on that. A proton interacts with a nuclei. Of course, it will be typically an oxygen or a nitrogen nuclei, for obvious reasons. This interaction will normally be hadronic interaction, so you produce particles, mostly pions. These pions can be charged or neutral, and of course, isospin symmetry tells you that about 1/3 will be neutral pions. And neutral pions means gamma decay, while the charged pions make strong interactions or produce muons by decaying weakly. Which means that a shower is always, in the case of a proton primary or in case of any hadronic primary, it is always the overlap of an hadronic shower plus an electromagnetic shower. The electromagnetic shower will be made of photons that will convert to electrons, so you have a cascade of electrons and photons, which is called the electromagnetic shower, plus a cascade of pions and muons, which is the so-called hadronic component. For reasons that are related to the cross-sections, the electromagnetic shower is very narrow. The opening angle is very small, because both the Bremsstrahlung and the Baire conversion are boosted forward, because it's all made by light particles. So being the energy very high, the opening angle of the shower is very small, and you have few effects related to multiple scattering, but they are not that big. So the electromagnetic component is relatively small. It's in the core. While the hadronic components tend to open because the cross sections are more peaked at large angles. First reason. Second reason, they are much heavier particles, so the boost is a factor 100 smaller, and so the opening angle is larger. So you have an electromagnetic core which is narrow and an hadronic core that opens more. If the primary is not a proton, but if it is an electron or a photon, of course, you have essentially only the electromagnetic component, not purely the electromagnetic component, because of course a gamma that interacts with the nuclei at 10 to the 16, 10 to the 17, 10 to the 18 electron volt can make, of course, hadronic particles, but the hadronic component will be much less. So it will be almost pure electromagnetic shower. The spectrum of the cosmic rays is that huge. It spans, as I told you, about 30 orders of magnitude in flux. From, you see the units, particles per square meter per second per sterradian per GeV. At 1 GeV, you have essentially kilohertz per square meter, okay? 1,000 particles per square meter per second is the typical flux of the 1 GeV particles that you get in space. This is the radiation that the astronauts get. These particles are mostly protons, with a component in iron plus a component in other particles. When you go to higher and higher energy, the flux goes down. The flux is controlled by essentially 3 different slopes. One slope is this first part, and then there is a bending that it's about here, in which, if you see carefully, this is one slope and then the slope change. This change of slope is called the knee. And then there is another change of slope, which is here, at very high energies. And this is second change of slope is called the ankle. This is just the terminology. What is more interesting is to observe that, as I told you, up to TV scale or something, you can make some kind of direct experiments. Then, here you cannot read, but it's Tibet here. You can start making atmospheric experiments at high altitude. Here it's Tibet, which means you have to go 5 meters above sea level to see these showers. And then you make detectors at ground to study the different energy. You see that the span is so large that you have to make a ladder of experiments. Okay? Each experiment sees some energy window, but you have the window of each experiment drawn in the plot. And of course, it's a big job to study the whole span. This is even more complex if you understand that also the composition of the cosmic rays is a function of the energy, in the sense that the relation between proton and other heavier nuclei is a strong and difficult function of the energy. This is not surprising because the accelerator mechanisms depend on the charge, but also the mechanism of energy loss and the propagation in the galaxy depend on the charge-mass ratio. So you expect the composition of the cosmic ray flux to be strongly dependent on energy, and it is. So each experiment provides usually not completely consistent result with others, because maybe just the energy window that he looks at is different. The extremely high energy cosmic rays are one of the most important regions and most interesting one, for reasons that I will tell you in a moment. This is essentially the same plot as before, with a different scale and with more explicit description of the change of slope that is called the knee. Currently, the knee is understood. The reason why we see a knee is that that energy is essentially the maximum energy that can be confined in the galaxy. Within the magnetic field of the galaxy, the Larmor radius of the cosmic rays in that magnetic field is smaller than the galaxy diameter before the knee and larger than the galaxy diameter above the knee. So below the knee, all cosmic rays are confined within the galaxy, so there is a kind of accumulation. While above the knee, the cosmic rays leave the galaxy, and so they are lost. So there is a decrease of the flux above the knee, and this explains this steepening of the curve. You have a more steep dependence of the flux from the energy, because higher and higher energies correspond to a loss of the cosmic rays in the galaxy magnetic field. So this is the standard explanation. We have instead a very poor or completely missing explanation of what is happening here. The general understanding, but this is more an opinion than a fact, is that in that region, we start seeing cosmic rays coming from outside the galaxy. So all the spectrum up to somewhere here is dominated by galactic cosmic rays, accelerated by sites that are probably supernova remnants or pulsar or other highly energetic places. The origin of cosmic rays is not completely understood. There are many models, but no clear explanation. While there are some evidence, but no proof yet, that extremely high energy cosmic rays come from outside of the galaxy. The main argument to believe that they do not come from the galaxy is that you would expect to see bright, well-defined individual sources at that energy. Because at that energy, the magnetic field of the galaxy cannot bend the particle. So you would have a straight line from the source to our observation point. And either the flux is very low, so you would expect to see the sources, to see accumulation of the particles under the direction of the sources. We do not see the sources, so the standard explanation is that these cosmic rays are very rare particles that come from very far away acceleration sites that are uniformly distributed in the universe. So if they come from very far, you can explain why you see no sources. But this is not proof. This is an interpretation scenario that still for a proof.
But what kind of sources could give such a high energy, like AGN?
We do not know.
No.
AGN is a typical candidate because we know that AGN are made of black holes that are usually rotating and so producing huge or humongous magnetic fields and electric fields. So they could be a good place to produce such a huge energies. But there is no model that in a serious and consistent way explains that. We don't have a model of an AGN that is more than a picture. We can draw a picture, but doing a calculation is a different story. And also, we do not have numbers that explain these energies. So yes, the typical answer is they come from AGN, but if you ask why, they tell you why not, but not much more than that.
Means that until you have a proof.
Well, you don't have a better candidate, so yes, they smell like the right place, but we don't know yet. Until we see sources, and we see a clear correlation between the sources observed with cosmic rays and AGN in the sky, we simply don't know. So it's still an open point on the search.
There is a range of energy where we can be sure about the source, the position of the source.
Well, it depends on the distance. The magnetic field in the galaxy is at the level of microgauss. But there is a residual magnetic field between the galaxies, which is believed to be at the level of nanogauss, which makes a factor 1,000 more in larger radius, but you still have a bending. So, and there is another mechanism that I will tell you in a moment that is called the GZK cutoff, which forbids to get 10 to the 20 energy particles from too far away. And actually, recent Auger data show that essentially there are no particles above the GZK cutoff. So you are limited to essentially 100 megaparsec. Above 100 megaparsec, the universe is not transparent to charged particles because of an effect that we will see.
So they interact with other particles before.
Interact with the photons, I tell you. We observe at low energies, you see, look at the scale of these plots. This is a scale in the low energy part. And as I told you, now you see more quantitatively, there is a chemical composition, so we see all particles. Of course, the dominant, it's a log scale, be careful. You see proton, mostly, dominant. Then you see helium. No surprise, these are the two most abundant elements in the universe, so you get those as dominant. But you have particles from other planets, which is a proof that the origin of these particles is probably related to places in which supernova occurred, because these elements are not primordial. So the fact that we have a flux of nuclei that are not protons or helium makes clear the fact that the likely place where this acceleration occurs is either supernova remnants or anyway places in which supernova occurs, so the chemical composition is not proton and helium, but you have something else. Actually, supernova remnants are the candidate for acceleration, at least up to the peak. Then it's not obvious to get higher energy cosmic rays from the knee, but the galactic cosmic rays are believed to be produced by supernova remnants, but it's not totally true. But this lots of this kind clearly give some strong argument, because all chemical elements are produced. And by the way, if you remember the production of elements in nuclear fusions during neutronization, if you have studied that, you recognize that they are the same element. So during these nuclei that you see are the same that are most abundantly produced in supernova. There is a good agreement between supernova and flux, but not complete agreement. This discrepancy is explained by the fact that there are some destruction of elements in the solar system, like for example the composition, the quantity of beryllium that it's in the solar system is much lower than cosmic rays. So there is this gap here, and there is the scandium-vanadium problem, so-called, which suggests that the origin in the solar system of these elements is not pure supernova, but there are some other effects which are not yet understood. But it's not impossible that there are other nuclear reactions that are relevant for the formation of the solar system. At very low energy, you see strong magnetic effects. This is an example of the flux you observe at the North Pole and at the equator below, in the 1 GeV region. Of course, 1 GeV, the magnetic field is relevant, and the particles are sent to the North Poles because they are driven by the magnetic lines to the poles, aurora borealis, and so the flux at the poles is much larger than at the equator by an order of magnitude. So So the proton flux at the poles is about 10 times or even 100 times more than at the equator. The west-east effect is clear from the shape of the magnetic field of the Earth. Don't need to go too much into the details. Just remember a few numbers. You have micro Gauss in the galaxy and micro Tesla in the Earth. So you have 4 orders of magnitude larger magnetic field around the Earth than the typical field in the galaxy. And you can try to remember this number, which is the number of kilometers, the Darboux radius in kilometers for a proton, if the field is microtesla. So for Z equal 1, 3,000 kilometers, which is 1/2 of the Earth radius. But for heavier nuclei, for higher Z, it's much less. So Z is 10, you have 300 kilometers. So you immediately are trapped by the magnetic field. Galactic cosmic rays are understood mostly, as I told you, as accelerated from supernova remnants. And in principle, what is called the multi-wavelength approach could help. In the sense that if you imagine, assuming you have detectors that are sensitive enough to detect photons, neutrinos and protons, you could check this model. Because the protons, you just observe the flux, but they will tell you no direction, because the direction information is completely lost. But if it is true that protons are emitted by supernova remnants, we should see, in principle, the supernova remnants in the neutrinos, because the production of these high-energy protons should make interaction here, produce pions that eventually will lead to neutrinos. So you expect a neutrino flux from the same sites that accelerated the protons. And you expect photons of high energy due to the acceleration of the electrons. The electrons will disappear because high-energy electrons will lose energy by Bremsstrahlung very efficiently. So you don't dream to see the electron, but you can see the secondary photon. So a combined, what is called now, it's very popular, the multi-wavelength approach, or the multi-messenger approach. Ideally, we can check this model and understand this physics or this astronomy, you can call it as you like, by a combined analysis of these photon plus neutrino plus proton plus eventually gravitational wave observation. The same from extragalactic. Where acceleration might occur? Well, this plot in some typical form was done by Elias a long time ago, which is not completely correct in the sense that it's very crude and very simplistic. But gives you the idea. The maximum energy you can build with a magnetic field using a Fermi model of acceleration, either shock first order or second order, is that roughly that. Z is the charge of the particle, beta S is the velocity of the shock of the supernova remnant wave or any kind of shock propagated into a field, B is the field strength, and L is the typical size of acceleration, the amount of space that you have to accelerate. This is very rough because it assumes that you have no dissipation of energy of any kind, which is never true. So none of these sides actually work. Okay? None of these sides explains the energy we see. But this gives you an idea. 10 to the 20 electron volt proton is out of business for all. Interesting. We really have no explanation whatsoever. 10 to the 20, we have very little events, but some are there. The 10 to the 29 or so can be obtained by a few sites. Either because there are super large magnetic fields like neutron stars or gamma ray bursts, in which you have a small object but with really super large magnetic fields, or you have very large objects like an entire galaxy or a galaxy cluster with a much smaller magnetic field. These are Gauss, so I told you micro Gauss is the typical magnetic field of galaxies. Okay? Intergalactic magnetic field, IGM, is here. This is optimistic, it's more 10 to the minus 8 or so. This is 10 to the minus, it's 2, because this is 10 to the minus 7, 10 to the minus 8. So these are the possibilities. The AGN are very nice. They are large, but not huge. They have a very large magnetic field. They could be a good candidate. People like the AGNs of this region because they fit very well the plot. At least up to 10 to the 19. 10 to the 20 is not really understood even for that. GZK effect. Why the universe cannot be transparent to very high energy charged particles? The reason is simple. In the universe there is a large amount of photons which are produced by the cosmic microwave background radiation, which is the primary radiation originated during the formation of neutral hydrogen 300,000 years after the Big Bang. When neutral matter formed, radiations decoupled, the universe became transparent to radiation, a large amount of photons started to propagate freely in space, and these photons are still there. And they are now seen thanks to the red shift due to the universe expansion. They are not anymore 13.6 electron volt photons, that is what is produced in the formation of hydrogen, but it is radio microwave photons with energy that is a factor 1,000 less. These photons are there, so when a proton propagates in space, can interact with these photons. You would expect such a photon to do nothing, but if the boost of the proton is large enough, if you have a 10 to the 19 electron volt proton, you can easily check that the invariant mass from a very low energy photon, a fraction of millielectron-volt photon, with a proton whose energy is above 5 × 10⁻⁹, which means 5 × 10⁻10 GeV, which means that the relativistic factor is 5 × 10⁻10, okay, gamma 10⁻10.